velocities are moving it. At the very bottom, some of what we produce, including the oxides with the metals and compounds, bicarbonates and so on, downwell to the, and are lost to our domain, to the lower atmosphere. And I'm not complete in the list of constituents here that are involved, but it's a fairly complex, detailed situation that we have to, that needs necessarily to be modeled and understood. In the lower right, I have an advection process, not diffusion, but advection, that also contributes to some extent to the constituent rarefication and richness of how much oxygen more or less is coming into this region we're discussing via upwelling and downwelling in a seasonal sense, summer upwelling and winter downwelling. So that adds to the complication, but certainly a modeling process that needs to take place along with good knowledge of data and so on in this region. We take cuts and pieces of this, and mostly I'm going to talk about just the eddy process today, the far lower left. Next. Okay, so in addition to the transport, this just shows a bit about the dissociation rate from the FUV from the Schumann-Runge SR continuum. That's a heavy curve on the right. And the Schumann-Runge bands are shown in that heavy dashed line all the way down to the stratosphere. So some O2 is dissociated, making oxygen all the way down to the stratosphere and to somewhat into the MLT region, which we're discussing. The oxygen, if you look at the lower right, that greenish curve, that's a plot of the recombination. That's where O goes back into O2 with a three-body process and peaks near 87 kilometers. So part of what I'm going to discuss with the transport process is we dissociate above 100 kilometers. The centroid height for the continuum is up around 113 or 111 to 113 kilometers. And you'll see that there's a EUV product up around peaking near 120 kilometers. That's also responsible for a lot of other dissociations, not just O2. So this is primarily the O cycle that I'm going to talk about, O and O2 today, which is a key constituent to the mesosphere and thermosphere and the catalyst to all kinds of the chemistry going on. So next. So first I'm going to talk about this method, and it follows from that last chart I just described. So the next chart is on the left, we have the premise of dissociation occurring above 100 kilometers, actually a centroid of 111, 113 kilometers. And then we have a downward flux of atomic oxygen, N sub O, combined with the eddy and molecular velocities that contribute to the total velocity or downward flux, to a chemical loss where the recombination is occurring at a peak of 88 kilometers. And so this is, there's some minor holes in this. We know that some of the O is made down in the mesosphere by the bands and so on. So to the first cut, this is an upper limit of the eddy coefficients and would be reduced by how much is made locally, but generally pretty solid. The other thing I'd like to chat with a moment about this at this point is what goes on in the MLT region is much slower in the way of diffusion implementation than it is in the thermosphere. When you have a constant boundary condition at 120 kilometers, as the old IKEA model had, for example, you're talking about a few hours to maybe 6 hours delay before you have a change that in diffusion time would show up at 400 kilometers. In the mesosphere, it's much longer. This Linetsky did a nice experiment using solar rotation in 2017, where he associated or correlated the solar rotation of an active spot on the sun with an additional amount of radiation, then showing up down at the recombination region, or excuse me, first of all, at the green line altitude, which is about 97 kilometers, and found it was almost 2 weeks. We've calculated that it would take another 7 days to show up before it would reach down to 88 kilometers, where it shows up at the altitude where recombination takes place. So this is a 3-week time period. So as one looks at processes of chemistry that are going on, these are the time constants that we worry about when we're doing analysis of data and processes that are going on the sun and showing up in this part of the atmosphere. So the next chart. So this is the method we used that we'll talk about on the data for the analysis of SABRE. We divided the year into 26 2-week periods and 3 zones. We have a northern hemisphere plus 15 to plus 55, the equator plus and minus 15 degrees, and the southern hemisphere minus 15 to minus 55. In each zone, for each period, we took 16-year average SABRE O density from the most recent SABRE database that's online, 2002 to 2018, actually. And we've also processed data for 10 years of Skiamachi, which also began in 2002 to 2012. So the Skiamachi data overlaps the SABRE data for the early years, and so it's in the same solar cycle domain. So as we look at those chemical coefficients, we need O, of course, so we're getting that from these respective satellites. And then for the N2 and O2, the background atmosphere, the temperature, we're using the NRL MSIS, the most recent one that just published this last year, version 2.0, which contains the N2, O2, and T data that we've used in this analysis, and used them for the appropriate time of year and the appropriate latitudes for the respective analysis. So if you take those 2 items and understanding the zones, we'll go to the next chart and I'll talk about number 3 there. So this is the, in the simple sense, the chemistry, the few equations that are involved to solve the for the KZZ. The second equation defines the downward flux of atomic oxygen based on the fact that from 80 kilometers, we're assuming that little or no oxygen goes below that, that is of much meaning, up to the altitude of interest, that the total loss that goes on through the chemical recombination has to be driven by the flux. And so the other 2 terms, the first term is the one we talked about from the earlier chart. And those second 2 terms, the middle K4 term is from 3-body oxygen recombination up near 97 kilometers. And the bottom one, the next one there, K6, that has to do with HO2. Those 2 terms contribute less than 6% of the total integrated contribution of loss. So for big picture of things, the first term is the main one. So once we have determined that flux, we can divide the flux by, that's the total flux. And so if you go to item 3, the total flux is equal to, excuse me, the eddy flux is equal to the total velocity minus the molecular component. At the top curve, we have, or equation, I should say, the flux is also in the two-part classical terms, where the molecular diffusion coefficient, d sub I, is on the left, and kzz, the eddy contribution, is on the right. So those two terms are separable, and as we follow down from the eddy term on the top, we can rewrite that in equation 4 and solve for the eddy diffusion coefficient, kzz, in terms of the eddy velocity and the atmospheric parameters of scale height, temperature gradient, and O density. So with that, we can move on to talk about some data. So the first thing I'm going to talk about is the interannual variation of kzz at mid-latitude, or the annual oscillation, as we'll see, and equatorial oscillation in the SAO. Okay, so this is the, excuse me, the altitude, 80 to 95 kilometers versus day of year for the northern hemisphere, the top panel, and the southern hemisphere in the bottom. And this is all from the SABRE data. SABRE data goes up to 96 kilometers. That's the limit of OH, and we're pushing it as we push it down to 80 kilometers. But this is the results with a linear scale of kzz. And of course, we in atmospheric dynamics look at this and say, wow, that's an annual oscillation, and that's all I see. And of course, it's symmetric. The northern hemisphere summer has the maximum up near 2 times 10 to the 6th with a maximum below 85 kilometers. And the southern hemisphere summer is also the same. It's just very much a mirror of what we see as function of day of year. The other thing I'd like to point out here is that when we talk about the annual oscillation and the traditional source of the meteorological conditions from below and the filtering that goes on in the stratosphere that has a birthday with summer and spring equinox, if you look at day 80 and day 285, those are very close to seeing some amount of annual oscillation appear in the respective hemisphere. So I would say that when I looked at this, this is classical textbook. I mean, what would you say that the annual oscillation is driven by the very meteorological conditions that we expect, where gravity wave filtering, allowing the once the stratospheric winds turn around to be easterlies, and enabling the westward directed waves to reach the mesosphere, they go to work. So the next chart, well, this is the chart on the left. This is just a plot of the amplitude of that variation with day of year for 4 altitude regions. The big solid curve is at 83 kilometers. On the right, I'm just showing the squares is what the Skiamachi data shows for its, when we've analyzed kzz from it. So they're very much the same. Skiamachi data has some, didn't do what we call a orbital turnaround every 60 days like SABRE did, and as such, they're much more susceptible to having solar effects obscure the instruments during certain periods of observation, and thus we'll see much more patchy and making much less a contribution. As a result, we don't use the Scaramucci data in this analysis in our global means, which we'll talk about later. So next is southern hemisphere, the same charts. The solid curve is southern hemisphere at 83 kilometers. And on the right, you'll see again the northern hemisphere as the central peak of the AO, and the southern hemisphere is the dashed or saber. And also now you'll see that the southern hemisphere squares, Scaramucci has data for the winter part of the southern hemisphere, but not much into there's a square right on the intercept with the northern hemisphere, but where we have data, there's a coincidence of the same values of KZZ. Next part, next curve. This is, so we did find, this is right at summer solstice and for the winter and the summer for Sabre and Scaramucci. So if you look at the solid curves are for Sabre and the dotted are Scaramucci, you'll see that there's some differences below 85 kilometers for the magnitude of the Scaramucci data versus Sabre. But the change between summer and winter is the factor change is about the same. And again, above 90, there's little or no change. Notice it's all below that. So one of the things we did was we looked at, if you take the winter to summer solstice KZZ values and you go back to the model, we could compute how much, what's the difference in the flux from the 95 kilometers altitude region and below. What's the difference in flux that corresponds to the difference between summer and winter? So as we go to the next chart, we found that the flux difference to account for that solstice difference in KZZ would be about 20% at 96 kilometers. The solid curve here is a measurement of what we did quantify as a downward flux at 96 kilometers for day of year for the northern hemisphere. And that arrow you see is what we calculated would be necessary to account for the difference in KZZ. So there's some differences, especially in the spring, that we'll be discussing shortly. So next. So on this chart, we have KZZ versus day number on the left. We've talked about those. And on the right, we have the O density versus day of year for the respective hemispheres. So the first thing I would say is that when you look at the northern hemisphere and southern hemisphere, in both these cases, again, it's classical. You have enhanced KZZ on the left, and you have a huge depletion where the depletion, the density here is percent from the annual mean of density in the respective hemisphere. So, of course, we see that there's a 50% reduction at the center of the annual oscillation in the northern hemisphere when that KZZ is maximum. And of course, it's what you would predict, classical. It's doing what we thought it should. Also, the southern hemisphere is doing the same thing. In the winter, we see a lot more atomic oxygen and the depletion than in the summer in the southern hemisphere when the KZZ increases in the summer. The other thing I'd like to show, if you look at 90 kilometers near day 180 on the northern hemisphere, you'll see a dotted curve coming down from an event we call P2. We said, gee, what is that? So that's a bit unusual, and you'll see that it shows up in both hemispheres. 180 days later, it shows up in the lower right in the southern hemisphere. And it appears that it could be that real trough would show up as a extension of the loss in the lower atmosphere and in the lower part of the region below 90 kilometers. And then for this brief 3 weeks to a month, it just pokes up into the upper part of the MLT region. But this is the first time we've we looked hard at this to understand if it was geophysical versus some artifact of the measurements, but here it is. So next. So one of the things I would then just point out, as we introduced very early in that very first chart, the consideration of the residual circulation and what's that's doing to a respective summer hemisphere. And the residual circulation has a upwelling in the summer. It brings low density, low mixing ratio O density upwards. So it's rarefying the atomic oxygen above 80 kilometers, just as the enhanced eddy diffusion activity going on. So both of these act together to do the same thing. We don't have a factor as to how much one contributes to the other. What we expect this one is considerably less, but we simply don't know. As this lesser amount of, or this rarefied O upwells into the MLT, we know, of course, that this circulation closes on the winter hemisphere and downwells, causing the opposite effect. So this is, I think, a big activity, or excuse me, a major issue that I think the modeling community really needs to go in and help best understand what's going on here and what contribution the upwelling of the residual circulation makes to the overall rarefying we have that we identify with the annual oscillation. Next. Okay, now we're switching to the equatorial region. Wow, you look. So we'll switch charts in a moment, but to the left you'll see the 4 altitudes. The solid heavy curve is 83 kilometers, and the other dashed lines, the dotted curve is down at 83 kilometers, the lowest altitude, where the annual oscillation has been huge. So now we see a very different picture. At the equator, the SAO is acting to be quite minimal down at 83 kilometers, but almost of equal magnitude above. If we look on the right panels, there's at the top at 96 kilometers, there's some semblance of what the Schemachi tells us is the same values, the same trends in amplitudes, but less alignment with amplitude. And on the 83 kilometers, there's little correlation, I would say. But we notice at 83 kilometers, there's little variation in either channel. We're talking about 10, 20%, not factor of 3. So in the next chart, we now look at the same chart that we looked at with the other two, and you get a better picture of what the SAO looks like in the top right panel. The spring amplitude is a half again larger in amplitude than is the fall equinox in the SAO. And it's there seems to be some phase relationship with that. But the big surprise here is the following. You'll see that in the spring and fall, when the KZZ is maximum, the density also is above the mean significantly. It's that way in the spring, and it's that way in the fall. So one thing to note is, of course, this enhanced KZZ is reaching well up into the peak of the O layer, 95, 97 kilometers. So as you're starting to drag density down, you're really pushing down a large flux. So the way I read this is that you're pushing down atomic oxygen in this SAO at a rate that's faster than the recombination down below is getting rid of it. It's doing that in both the spring and the fall. Whereas if you look back at the AO, those vertical extents don't extend much above 87 kilometers. They're not getting up to the region where you really have some O to bring down. Whereas here, that's what's going on. So this is a counter to the ideas we've had historically as to what would be happening to O, at least from the global mean at that particular altitude region. So next. Okay, so here I got a few charts to compare what these global averages. Next. So this is just on the left, we just have a summary of the KZZ in all three zones. And on the right, we show the density variation at 96 and 85. And note that those northern hemisphere, southern hemisphere show the P2 event. And if you look at 96 kilometers, you see that big spike near day 160. That's a very spike that is associated with the P2 event back on the chart, northern hemisphere upper left. Next chart. So this is the KZZ versus altitude on a linear scale. And note the northern hemisphere, southern hemisphere lay one on top of another. No surprise based on what we saw. And of course, it's on the global average now, where we're averaging summer and winter. The two hemispheres average to be very similar. Whereas the equatorial region, it's something close to 1 times 10 to the 6th, a little bit larger down lower, but quite different from the mid-latitudes. Next. This IAV study, that's the solid curve. Here we're putting this as for SABRE, of course. We're just plotting this on top of the data that we published back in the S19 data, the Skiamachi, KZZ, the SABRE, and of course the CO2 data from that study. I think we well understand it's a challenge to get the O density out and the shape of it. The CO2 analysis by Salinas and et al. And in our S19 paper, he did the CO2 analysis to show what we think what that data showed coming out of 80 kilometers. And so there might be some better understanding between the two of those as to what's going on very low. So next. So if you go back to the O density data on the left, and you take the three zones: equatorial, northern hemisphere, southern hemisphere. And when we take what we call the global mean there at 96 kilometers, there's not much variation over the course of the year. And those large red circles, when we did that mean, it's area weighted by the area of the respective zones, as the equatorial region was a lesser area than were the mid-latitude zones. So it's been area normalized. So on the right, we have the same thing with KZZ. The dotted is the KZZ over the course of the year. And of course, as we know, the annual oscillations are huge seasonal variability. So when you put those two together from the respective summer and a winter hemisphere, they average out to almost nothing. So thus the dotted curve just has a remnant of some SAO in it as a mean contribution. And the solid curve, of course, is from what Kian et al. Did in 2009. And of course, that study was done based on thermospheric input versus stratospheric versus mesospheric climatology. There's no, I should say, the difference here is attributed to how they were taken, not for, so the challenge is to explain what are the real differences to make this understood. So clearly, I think the bottom line is you just don't do global averaging. Just isn't the way to go about this, just because the seasonal variations in a given hemisphere are so hugely different that you just have to go to respective hemispheres and deal with the day of year and not try to average them out because you nullify everything. Next. Okay, so getting there. All right, so lastly, I'm going to leave the discussion now from Saber and Skiamachi and talk about a bit of LiDAR data and what I think is the data is suggesting, at any rate, about KZZ in the zones, what's going on with altitude. So in fact, I think Han Li, some years ago, when we had the discussion with Gold and Icon coming along, posed the consideration that, hey, what's going on? We see a lot of turbulence up above 100 kilometers in the density data. And so what I'm about to show is Channing Philbrick, the master's student with us, tackled the analysis of KZZ from Chile LiDAR data and provided some new insight to turbulence and KZZ at those higher altitudes. So next chart. We know, of course, McGow's work from 2002 and a few papers since, that from the chemical releases at all altitudes, or latitudes, I should say, we have a spaghetti plot of high winds and turbulence and shears, especially in the 110 kilometer region, peaking here probably 107 thereabouts. And so we've known for some time that these shear conditions and high winds are present. Next. So here's a few charts from some sodium density data. The one on the left is one of these overturning. If you've ever been to the beach, there it is. The waves are coming in, breaking and overturning. This one at 105, 110 kilometers. This is not an uncommon situation. We've seen those at LiDAR when we had it back in Urbana, and this happens to be observations from Chile in 2020. On the right, we see it in a different form, in a mixing ratio, the sodium density with respect to the N2 density. And likewise, we see topside disturbances above 100 kilometers with a lot of structure and instabilities, or results of instabilities. Next. So one of the analysis done by Guo et al. Was published in 2017, and I think this was the first measurement of turbulence and gravity wave spectrum from LIDAR that was done at Chile. And what it shows here is the slope of the power in the spectrum of gravity waves that separated primarily at the Brunfeisler frequency for the larger scales from eddies above a few hundred meters and to those of turbulence less than a few hundred meters in spatial scale. So there are two zones, and if you take the ratio of what's going on in the eddy zone to what's going on in the turbulence zone and making some understanding of what contributions are from those respective zones to heat flux and constituent flux. What's going on? Next. So here, if you look, I've got a schematic of a potpourri of a number of observations here, but looking at Gardner here, 2018, he had a plot there with altitude from 100, roughly 97 to down to 85 of turbulence only that he made from the Chile observation, but also from the observations made out in New Mexico with our LIDAR. And he has a turbulence only plot, and then he has a dotted plot of turbulence plus gravity waves on the which follows from that on the right. So if you look at that, of course, as you get up towards 97 kilometers, those two next down to having little difference. Turbulence dominates up there. But below, especially if you get down to the lower region near 190 kilometers, gravity waves dominate over turbulence by a factor of 3. So what Channing has done, Channing Philbrick, he's analyzed some 25 nights of LIDAR data for deducing KZZ from this is from this is the mean. Those diamonds are the mean KZZ from his 29 nights of data from ALO. And we do that here because we're not comparing to other sites or global means or global data here. We're looking at data right over a particular site, and thus we're keeping our comparisons local to that. So I've also plotted the molecular diffusion coefficient there, or excuse me, not the coefficient, but the amplitude. And you'll note that what's interesting to me is you look back at the KZZ term values, they kind of neck down near 100 where they're all equal, but then eddy takes off again with the turbulence only values with respect to the molecular diffusion. So it's interesting that in Channing's work, he has only analyzed the turbulence only. We haven't yet had the opportunity to go back and understand, is there an eddy component in the data? We don't have the data from the Doppler method that Gardner uses. It doesn't push that high. That's the whole reason that we've gone to getting the data out of this density only data. So I think, a question on the table is, do we have two zones going on here where this upper zone is really driven by shear instabilities and KHI processes, Kelvin-Helmholtz instabilities and so on, and leaving a turbulence only spectrum of transport and less so of the turbulence gravity wave component that we have below. So the last chart, I'll skip this one. I wanted to, I'll just spend a second on this. So you'll see the phasing of this. This happens to be data from when we had the instrument in Hawaii, 20 degrees north instead of 30 south. But you'll see the dominance of phasing, downward phasing of stability parameters and of instabilities above a region where there are stable and unstable regions, one on top of the other, with the Brun-Feisler frequency n squared and shears and shear instabilities. So these are truly present at low latitudes, and I just want to say that tides, especially the diurnal tide, has a big part in these instability conditions. I think the downward phase propagation here is at kilometer per hour, consistent with the diurnal tide. And that's a dominant forcing part of this upper altitude turbulence region, I believe. So last chart. So in summary, we have one, both KZZ and O densities have a large interannual variability, intraannual variability. AO dominates with a summer maximum at mid-latitudes. Number 3, the SAO is a dominant at the equatorial latitudes with a spring value considerably larger than fall. And the large mid-latitude AO has similar amplitudes in both hemispheres, canceling and cancel, which shows up in a global mean. And so I think in the last, number 5 is recommendations are to incorporate seasonal variations in KZZ and O densities for their respective zones as we move forward. I'd say the very last thing, I think what we're doing here, I think, is probably not necessarily a consideration to incorporate these directly in models, but as we are growing with our ability and WACMs and so on to move with vertical fluxes of turbulence from below and so on to drive what real KZZs are those similar to what we're getting up at these higher with these global means that we've found with this kind of analysis. So with that, I'll take any questions.
Okay, thank you, Gary, for a great presentation. To dissect this very complicated mesosphere, lower thermosphere region. Yeah, so any questions? Yeah, so I will start with, I have a lot of questions. So I will start with ask a question. So one thing that I didn't know before until I heard your presentation is the KZZ and the atomic oxygen is opposite in the lower altitude, like below probably 90 kilometers. Oh no, it's not. It's in the equator, in the equatorial region, KZZ and atomic oxygen is the opposite. When KZZ is large, atomic oxygen is density is low. But in the northern and southern hemisphere, they are no.
No,
in the equatorial, they are in phase. Yeah. I'm sorry. Yeah, but in the northern and the southern hemisphere, they are opposite. So I didn't know this before. So what this is telling me is the difference between the equatorial and the mid-latitude is because in the equatorial, the KZZ, the large KZZ goes to the higher altitude.
Yes,
right?
Yes, exactly.
Yeah.
So here's what I think is, so one of the things I think that's going on here is you go to the equatorial regions, the stratospheric filtering doesn't become as prevalent, or if at all. And I would say, thus, whatever's there in the easterly and westerlies spectrum of waves from mostly the ITZ there, that's just coming up to a higher altitude.
Mm-hmm. And then in the equatorial region, because the KZZ goes to higher altitude, and those larger KZZ can transport the atomic oxygen that is produced in the thermosphere down into the mesosphere. So that's why they are in phase.
I think so. Yeah, I think that's right. I think the fact that it's getting higher near the O peak, that is on average, the O density maximums at 97.6 kilometers. So because they have a large KZZ up there, you're really pushing some down.
Yes. So and that effect will reflect in the density and in the thermosphere ionosphere. So that would affect the thermosphere ionosphere.
Exactly.
Yeah.
Well, I think also how should I say this? Just lost my train of thought there. But yeah, so I think if you look at the summer winter middle attitudes, KZZ comes a maximum below 86 kilometers, where it's already on the downward slope in the loss region, and so you're not pulling anything new down there. You're just eating up what's there.
Yeah.
Yeah.
Okay. So here, Han Li has a question. Let's see. Han Li want to show the four equation. And Han Li's question is in equation 3. What vertical velocity is used there? Let me go back to that slide. Yeah, here. So the equation 3. Equation 3. What vertical velocity is used?
Okay. Yeah. So the vertical velocity that we use is we calculate the flux from equation 2, and then we divide that total flux by the atomic oxygen density for its respective zone, and deduce the total velocity from that. Okay, so in equation 2 we have the flux. So imagine that you can compute the flux profile from all of the zones and the zones and temporal periods that we have over the day of the year. And for each of those, we have an atomic oxygen profile, and we divide that out, and we have a profile of diffusion flux.
Mm-hmm. Okay, so I guess I have a question on this slide too. So is this, are you assuming that the flux that is transported into this altitude region by molecular diffusion and eddy diffusion, so this flux equal to the loss through chemical reaction?
Exactly, yes.
Okay.
That's correct. So it's a total flux, and the contributions from that total flux to the total flux are both the eddy and molecular components.
Mm-hmm. So is this atomic oxygen is all from, transported mostly from higher altitude to lower altitude, I guess, in this region? Or there's other way?
Well, yeah, okay. Yeah. So in the final chart, I should have attached, I think I did, which is the number of references that I had there. But we have a paper, S18 was the interannual variability. And in that plot, in that paper, we did have the terms plotted and for the solution to the equations. So at any rate, that's
Okay, so Hanli has a follow-up question. Hanli, would you like to ask this question yourself?
Okay. Gary. So I was wondering, when you calculate, use equation 3 here, you exclude the molecular part of the flux. But I was wondering, did you exclude the part due to mean wind or mean advection?
Yeah. No, we did not. The only contribution we've excluded here is from molecular.
Okay, so that means that the actual added diffusivity could include the effect from the advective or the circulation part.
It could, yeah. So,
Okay.
yeah, so I think, one of the things I would say there, one of the things is you go back to diffusion times, and let's say you have some anomaly in the distribution with altitude where some winds have been coming, giving a different distribution. Then over time, diffusion is going to extend from 110 kilometers and equalize it in this down to 87, 85 over a course of 3 weeks. So I think you again look at transport times and processes that in this analysis, which is a dimensional analysis, it's you have a process that on the average is distorting that profile from an advection component. Whatever's showing up in the distribution of average O density for 2 weeks is what we've assumed is eddy and molecular diffusion maintained. So I would say that in the sense that then this the eddy component that we have here becomes a upper limit of diffusion process.
So basically, this is assumption is a vertical advection, say, also transport. So when you do the global average, you're averaging them out, so there's no vertical.
So in the first papers that we did, of course, averaging out the entire globe, even meridional, or I should say, transport from the residual circulation across a given planet, or hemisphere, when you average out that for the whole year, we argued that, well, all those advection processes have to be a net zero contribution because you're not moving mass one way or the other, and thus diffusion prevails. But in this case, the questions are, I think to go further than what we have, we need to work with models together. It becomes a modeling process.
Mm-hmm.
I think next.
Yeah. Okay. So we are past the time. There's 2 more questions here. So Stan, you have a question. Stan, would you like to ask yourself?
Oh, sure. Hi, Gary. I just wondered if you could say in general terms how KZZ is derived from the satellite observations.
Yeah, I mean, in general, it's from the satellite observations in very general terms, the O profiles, the gradient of O is the driving component. If you look at this very expression we have here in front of us, I think the O density doesn't make a huge difference. At 10% in the profile density, if you uniformly add 10% across the entire profile, you add something like 1% change in KZZ. It's the gradient in O that's driving the sensitivity to KZZ, and that's what what's driven by the loss of O that we have, and if the gradient increases, means you're pushing it down faster than you're able to eat it up. But it's the net aspect of O density versus altitude that derives the KZZ. You know, I have to say one very nice paper from the early Garcia and Solomon paper, Rolando. They put a profile comparison of the gradient of O in their paper, and of course, rightfully so. You can actually see it visually in the illustration they made in their 1986 paper. So thank you. This paper is a step of a contribution, I think, to what they did so nicely back in 86 or 89. Does that help, Stan?
Yes, thanks.
Okay.
Yeah. Okay. So last question, really quick. It's Astrid's question. She has left the meeting, but real quick. So Astrid's question is, so she says you use MSES into O2 and the temperature to derive the KZZ, and were inconsistent with the observed O influence the result?
Yeah. So, I think we did not. We independently went back and used the O densities that we took off of for SABRE. But you should say that now that as you look at the ENSYS model, they incorporate all of the O densities and so on from SABRE into their model development. So I guess the first result was we didn't compare to the numbers that we got out to what ENSYS would say it is. And I would think if we did that, you could probably today you could use ENSYS. When we started this, ENSYS 2.0 wasn't there. Is that helpful?
Yep. Yep. Okay. So since we passed time, so thank you. Thank you very much for a great presentation and the answers all these questions.
Well, thank you. It's been a privilege.
Okay. So that's it for today. Thanks, everybody. And let's see. So Gary, actually, would you please stay for a little bit?
Sure, I can. Yeah.